Hub, and I'm going to be moderating today's session. So I'll just begin by giving some brief background about the West Hub. So we're led out of UC Berkeley, UC San Diego, and the University of Washington, and we're one of 4 regional big data innovation hubs funded by the National Science Foundation to build community that both advances and accelerates societally beneficial applications of data. And in response to regional needs in the Western US, water represents one of our hub's main thematic areas of focus. So the event today is really intended to promote an understanding of both the challenges and the opportunities associated with harnessing multidisciplinary data and AI-driven capabilities for water, and in particular, their potential role in furthering more equitable community water system solutions. We have 6 exciting presentations lined up about a variety of different projects and focus areas within this emerging space. We're going to have a Q&A session that'll take place at the end of all the presentations. You can feel free to add your questions into the chat throughout the event. We'll keep track of those. And also at the end, you'll be able to unmute yourself and ask questions directly during that segment of the event today. This is only a 60-minute session, so we might not be able to get to all the questions. If the presenter feels comfortable sharing their email address to field questions after the event, then they'll put that contact information in the chat at the end of their presentation, and you can feel free to reach out to them directly. So we're going to update the session's webpage after the event with additional resources like the recording of today's session, and we hope that you'll want to continue to stay engaged. So if you're interested in connecting on these topics in the future, we encourage you to fill out this Google form. We'll go ahead and drop the link to that form in the chat now, and we'll drop it periodically throughout the event before the session ends. Before we launch into the presentations, we're just going to do some interactive introductions on Menti. So to get over to Menti, you can either use your phone, go to your camera and scan the QR code, or you can type in menti.com, and then when prompted, you're going to input the code 14293254. I'll just give everybody a second to get there if you want to use the QR code. Then when I get to the actual Menti presentation, the access information that you can manually input will be available there too. Okay, so I'm going to go ahead and get over to Menti now. So this first question, it's intentionally very broad. So where in the world are you? So this could be where you're physically located today, where you're from, where you live currently, or the communities you work with. These are really just the places that you feel most strongly connected to. You can add up to 4. We're just trying to get a feel for knowing where everybody is joining from today. We'll give about 30 seconds for people to fill this out. This is great. It looks like we have people from all over the world joining us today. We'll give about 15 more seconds on this one. Yeah, this is wonderful. We're so glad that you're all here with us today. I think I'll close this one in about 5 seconds. So if you have a last response and you haven't been able to put it in, go ahead and do that now. Then we'll go to the next question. Okay, so the next question, it looks like we've already been getting some responses on this one. So it's really getting at your interests in the topics that are covered today. So what interests you most about the intersection between water and data and AI-driven capabilities? And you can go ahead and input more than one open-ended response if you feel strongly about a few different areas. And we'll give everyone a little bit longer on this one. Yeah, these are some really great responses. We'll do about 20 more seconds. So if you have one last response that you want to put in, go ahead and do that now before we launch into the presentations. All right, we'll close this in about 5 to 10 more seconds. Okay, great. Well, thanks everybody for being part of that interactive part of our intro. It's time now to move into our presentation. So I'm going to pass it over to Alfredo for our first presentation.
Thank you, Ashley. Let me share my screen now. Okay, so thank you for inviting me to this meeting, and I appreciate your support during all these years that we have been engaged in different issues along the border region between Mexico and the United States. Today, I will present to you our latest research work that we're doing in a small community, agricultural community, in an irrigation district in northern Mexico, which is in the state of Chihuahua, at the border region in between the three corners of Texas, New Mexico, and Chihuahua. This region is really struggling for water resources. And I'm sorry, can you hear me?
We can hear you. I think if everybody can please mute yourselves unless you're presenting. Thank you.
Okay, thank you, Ashley. So rationale is that in northern Mexico, Chihuahua is the main pecan grower for our country, and we should occupies about 62% of the national production in the whole country. So most of those regions, or most of those agricultural areas and the orchards of pecan orchards are installed in a desert area. So in 2020, we break the record of production on the number of hectares that we have under production for our region. So most of this production is exported to the US and into China, and it's growing in the last couple of years, producing a revenue of some millions of dollars, and that's why it's so farmers are really interested on keep producing pecans in the region. However, consumption of water is really high for this type of crop, and because of the ET measures and high stress and low precipitation, most of those pecans, or most of those hectares, are irrigated by groundwater resources. So we have an estimate of 1.7 meters per meters of depth per square meter of area per year, which is a huge amount of water. So our idea was to use this technology and on multidisciplinary data gathering to promote and monitor real-time calculations of ET and soil moisture content using all these gadgets that we have available for us in our research. so we can save and preserve water without affecting the production of the crops and the yields and the income to the farmers. So Mexico has a National Commission of Agriculture, and they are focusing on 8 major goals for the next couple of years. And obviously, you can see on this slide, and apologize for having this in Spanish, but I will try to translate those. So the first box is technology on measuring and putting sensors on the field to download real-time data. And that's one of the areas that we are focusing with this project. The other area is the last box in the right corner on the top, which is digitalization of information and measurements. And finally, we are gathering data, huge amounts of data, temperature, precipitation, wind speed, and all these climatological data, as well as these temperatures on soils and humidity. And that's where we use all these informations to do modeling, prediction modeling, and calculations. So we base our project on Microsoft FarmBeats, which is a project that we submitted a couple of years ago with them. And they provided a little bit of funding to the AI Center here in Chihuahua. And the logistics is based on this small diagram in which we install the sensors on the soils. We have computer center linked to our connections to the internet. We upload those data, digital data in real time to the Azure cloud, and students do the calculations based on algorithms they are developing. Finally, we gather data as well with the drones and measuring NDVI and soil temperature as well, and other type of information. And all this finally goes to an algorithm, and the algorithm is produce an app that the farmer can download, which is an app that is developed on a user-friendly approach, so they can see in real time how much water they need to put on their farm. So this is the type of development that we did, and one important thing that you have to notice in here is the small circles around these trees, which is the micro irrigation, micro sprinkler irrigation system that we have. Each one of those has one micro sprinkler. Each tree has one micro sprinkler installed, and it pulls out about 36 liters per hour on the tree. And we are scheduling this irrigation based on the sensors that we have installed, which is this Sensoterra technology they have. And we have 6 measurements at different depths on soil moisture and 1 of temperature. We have done the soil maps to measure the texture and analyze the texture in the soils, and map out how many sensors we need to install in there. So this is very important because this is linked to the gateway in which we pull out the data on real time and put it in the Azure cloud, so we can see it on the computers. Right now, the trees are getting bigger, and we are measuring and changing the model to install a little bit more of sprinklers. However, you will see some of the results in a few minutes, in which we are really happy to see how much water we are saving on this region, on this system. So students are mapping with our drones, mapping temperature and NDVI on the computers, and they go and run the surveys, and they produce the NDVI maps on the bottom. Some other students are working on the algorithms, and we intake all this information from the field and store this information into our data lake and produce all these algorithms after they do the treatment on the data and doing the QA/QC information, and trying to keep up the information on good quality, and produce the analysis to eventually do the visualization on some applications and machine learning to see how we can do the models. So we have saved water so far in the last 3 years, an estimate of 85% of the irrigation water that is compared with the traditional flood irrigation system that everybody uses. So this is really encouraging for us because we are seeing, without affecting the development of the trees, how the trees are surviving with less amount of water just by measuring and applying the water in the right time and in the right amount of water for the trees to grow. So we need to see how in the next couple of years how much production they're going to be generating. But since all crops need to work on their field capacity, which is this curve that you see in the middle, and you will see the percentage of humidity on some of the sensors that we have installed. And this is important for us because the stress that the trees or any crop suffer because of the huge amount of water that they apply, or the permanent wind capacity that they have to support. So this is where you don't want to be the extremes on this graph. So you have to keep it on the average field capacity, which is in the middle. And the only way to do it through time is to measure this information. So the next steps for us is we just have talks with a company that is going to be helping us out with some digital bulbs to install and control everything. Irrigation and everything is going to be controlled on our cell phones based on the measurements that we're going to see. We are doing inverse engineering. We are developing our own sensors right now as we speak. And students are doing some changes in their original designs. And we were producing and improving some of these sensors. And we recently trying to train people to see how easy it is to apply and use the apps. Every antenna that we have on the field, it reaches up to 5 kilometers in diameter, which is important for the different areas that we have. So I think that that's the last slide, Ashley. I will put in there my email for anyone that is interested to talk a little bit more in regards to this project. And again, thank you for inviting me to this important meeting.
Wonderful. Thank you so much for sharing about the fascinating work that you're all doing. Okay, our next presentation is Akshay, you're up.
Awesome. Thank you, Ashley. Alfredo, that was really, really fascinating. I'm going to be taking a slightly different approach to talking about big data in water governance, and we'll be presenting, or I will be presenting on a set of insights that we've gained over the last 10 weeks working with NASA's GRACE data product suite. And the project I'm going to show you today, or at least the outputs, are actually the result of a intense collaborative effort that's pretty special. So I think it's important to just share who we are and to introduce the Data Science for Social Good program at the University of Washington, which is housed in the in eScience Institute. And the DSSG, which is what it's known as, is offered annually. It's been offered since 2015. It's a 10-week summer program, and there are about 2 to 4 projects per year. And these projects are basically built up of interdisciplinary teams. There are a set of project leads. In this case, there's myself and Samir Shah, who's a professor of climate adaptation in the University of Washington in the Department of, or in the School of Environmental and Forestry Sciences. There's also Linda Barrientos, who's our community engagement lead. 2 data scientists at eScience, Vaughn Iverson and Dharma Daly. And then we had 4 students. These are fellows that come from various disciplines. None of them actually have a background in water science, but they're incredibly talented and they have an interest in using data science for social good problems. And so working with these 4 fellows over the last 10 weeks, we set out to basically answer a really simple question, or to achieve a really simple goal, which is to build a flexible and well-documented workflow that can easily be used to study groundwater changes in the Colorado River Basin and in the future in other regions. And you'll notice that I've highlighted flexible and well-documented. And the reason I've done so is because those 2 concepts are so incredibly important to working with really large data, which are, for the most part, readily accessible, but really hard to actually then translate into usable outputs. And so one example of remotely sensed data that can provide insights into groundwater is GRACE. So that's a gravity recovery and climate experiment. So these are a pair of satellites that first flew in 2002. There's a follow-on mission that started in 2018. These two satellites orbit Earth and they record minute changes in speed and distance using microwave ranging. And when you take these distances and their locations and then you process them using a variety of algorithms, you can essentially get gravity anomalies out. And those gravity anomalies can...
Akshay, sorry to
Yep.
interrupt you. I think your slides are not moving.
Oh, are they not? Can
It's on
you...
the title slide. If you do
Okay.
control L, it'll put
Yeah.
you in the
Can you
full
see it
screen
now?
then. Yes, we can.
Okay, cool. So you all missed all of that, but okay, I'll just keep it in this format. I think that's the easiest to do. So in any case, thinking about GRACE, once processed, we essentially get gravity anomalies out of GRACE data. And we can use those to trace water movement. And here's a really nice figure that just shows the Amazon basin in the year 2004. And what you can see are changes in mass over time. And those essentially represent changes in the hydrological cycle in the Amazon basin. So there's a lot of power just inherent in GRACE itself. But the problem is that when you want to translate the raw data that comes from GRACE into those usable outputs, so say if you want to say something about groundwater, that process is rather complicated. And one thing that I feel very strongly about, because I work with AI/ML pipelines a lot, is that before we can utilize any remotely sensed data in these pipelines, or for that matter, for research, advocacy, or policy purposes, these data have to be pre-processed. And this pre-processing step is really critical. It's something that we sometimes skip because we say, okay, we can just download something and start applying it to some AI pipeline. But really doing that work is very important. And one example of this sort of translation is this idea of trying to calculate groundwater storage from GRACE. And so you can't just take GRACE data and those gravity anomalies and say, okay, that represents something about groundwater. Instead, what you have to do is you have to take the change in terrestrial water storage, which the terrestrial water storage is the product that you get out of GRACE. You have to subtract some snow water equivalent, some soil moisture, and some estimate of surface water. And as you'll see here, is you require other forms of data to do this calculation. So this is the first thing that the fellows confronted, which was just what's the equation that we use to understand groundwater storage? And having done so, then they realized, well, we have to actually go out and get GRACE data and GLADIS data and USGS data and put it all together. And so this is the initial workflow or pipeline that the fellows came up with. And essentially you just move from downloading the data, you process it in some way, and then essentially you can comprehend it. Now, the fundamental problem here is that any one of these steps are non-trivial. So when you go to download GRACE data or GLADIS data, it turns out there are 145 matching data sets when you type in the search word GRACE into NASA's website. They have 10,000 files that you can download for GLADIS, and each one of those files has 37 data variables. If you go ahead to try to process the data, it turns out there are multiple units of measure. They have multiple resolutions, so fusion of data from between GRACE and GLADIS and USGS is pretty complicated. And then the data in a geospatial format, which anyone who's worked with geospatial format data knows, it's not extremely easy to work with. And then finally, even once you've done all the steps of fusing everything together and calculating groundwater, what you get are changes and not fixed numbers. And those are hard to interpret, especially for non-experts. And what was really interesting was as part of their work on groundwater estimates, after their fellows had sort of set up this equation, what the fellows figured out was that there are 0 detailed guides online to calculate groundwater from GRACE data for non-experts. So if you're not a hydrologist, instead you're an advocacy person, or you're someone who works in policy, or you're like the fellows who are extremely talented with respect to data science and AI and ML, but haven't really worked with GRACE before, it turns out there's no easy way to just take the GRACE data, know which GRACE data to download, know which products to get, then combine them with GLADIS data, and then actually turn it into a usable product. And so essentially this became our driving goal, which was we need to create a detailed guide to just basically calculate groundwater from GRACE. And that brings me to this central point, which is that we need flexible and well-documented workflows when we're thinking about these large data sources. So when we think about remotely sensed data, whether it's satellite data or it's GRACE data or GLADIS or whatever it might be, we need not only workflows that are flexible, but also are well-documented. And in this case, the fellows built this workflow where we go from finding the right data sets on the left all the way to visualizing outputs on the right. And instead of trying to build a whole new software tool, what they did was actually create a series of Python notebooks in which anyone who's interested can go in, change a set of variables, and then be able to download the right GRACE data and go all the way to visualizing outputs. And in this way, we sort of reduce the overhead of actually trying to build and then update a full software package. The ultimate outcome is to take all the stuff you see on the left, so these are the websites and the tables and whatnot, and turn them into a usable product on the right, which is just showing groundwater volume anomaly in the Colorado River Basin as a raster. Something that's easy to interpret, something that people in advocacy and policy circles can also work with. And I've talked about well-documented workflows, and well-documented workflows are critical to sort of, are a critical first step towards AI/ML. And to that end, the fellows actually built an entire website where not only do they explain how groundwater anomalies are calculated, but they also work through a set of questions that anyone can go in and they can click on what is your question and understand this is what GRACE can answer, this is what GRACE cannot answer. Go all the way down to understanding uncertainty. So after you've done all your processing, what do you actually know? And then what is still unknown? This website is publicly available. I'm happy to share that in the chat as well, but it really does illustrate, I think, the importance of kind of working or documenting everything that you do as you work with these data. And so with that, I'll thank you for your time. Thank you.
Amazing. Thank you so much for sharing about that wonderful DSSG work that your team's been doing this summer. Next up, we have a presentation by Ilya.
So let me share my screen. Okay. And one second. Okay. Can you hear me okay? So my name is Ilya Zaslavsky, work at San Diego Supercomputer Center, and I will talk about one of the activities of the Transboundary Groundwater Resilience Project. This is an NSF-funded project to bring together researchers working on transboundary aquifers from different countries and from different domains, including hydrology, data science, simulation modeling, social science. In other words, build a network of networks that will leverage collective worldwide expertise in this critical topic. You see project members here on this slide, and some of them are in the audience today. Okay, so the topic is indeed very important. There has been significant levels of groundwater depletion in transboundary areas, and one of the reasons is lack of cooperation across the borders. There are about 600 transboundary groundwater systems, but only 6 of them maintain any formal cooperation, and only 1 has management agreement between countries. So how do we do this? How do we bring together these different groups of researchers? We started with a traditional way of building a network, connecting to researchers whom we know personally, organizing webinars, having an online modeling course, supporting students. And we also built an online system where people can enter their information and kind of put themselves on the map, so to speak, describe their projects, find experts with similar interests. You are very welcome to add your name to the system, and then you will be able to take full advantage of it. There should be links in the chat that would allow you to do that sooner or later. Yes, CT just published quite a few links, and you're welcome to try all of them and add yourself to our project gallery if you're interested. But this approach, building the network incrementally, has one very serious limitation. It's very difficult to get people to add their names to yet another online form. So our directory remained fairly small. And so we tried a different approach. Instead of bottom-up incremental building a network, we switched to analysis of everybody in the world who ever published on transboundary aquifers using data from a new large and open bibliographic source. Here you can explore the entire co-authorship network to see who has been working with whom and whether there's potential for transboundary collaboration and whether gaps, and you can see how this network developed over time. You can look at individual profiles and photos. You can see distribution by any variables, let's say by countries or by research interests. Look at the researchers on the map. Also see all of their relevant publications and determine how central these researchers are to the system using various types of indexes of centrality, clustering, key player fragmentation, and so on. The source of this information is, oh, okay, so wrong click. The source of this information is a new system called OpenAlex. You can explore it online, openalex.org. It indexes about 400 million publications in multiple languages, journal papers, but also preprints, technical reports, and other so-called gray literature, which is often very important to understand what's going on in hydrologic and aquifer research. So we organize this data at SDSC, and so that we can consistently query them and generate network visualizations and network analysis systems essentially on the fly based on any combination of keywords that you enter. So you can search for any papers that mentioned in abstracts or in titles terms like transboundary groundwater, transboundary aquifer, binational aquifer, or things like that, and it will return the entire network for you to analyze. And you can also specify additional keywords that you want to tag this network with, add a bunch of static layers, and so on. So I can show you how it works in live, but this is just a video I captured last night. Basically, you can follow the links and try it yourself. We have a gallery of all researchers. There are about 2,500 people. For any of them, you have sort of a profile where you can see what topics the person has been interested in, look at the collaborators, look at, and by the way, here I entered the name of our moderator, Ashley, and we have her picture because she also worked on this topic. We can look at any characteristics. So for example, here I'm sorting by country and I select which countries I want to show in the view and to see where the researchers mostly come from. Then in our case, we're mostly working on collaboration between Mexico and the US. So I zoomed in on Mexican researchers. I can click on any person and again see the metadata, collaborations. I can also show all publications and look at the abstracts and sometimes the publications themselves. In addition, we can see where these researchers are located in the world. These are clusters of researchers. We can kind of uncluster them, and yeah, I guess in this case, Google Maps was a little behind my attempt to show it quickly. But so now you also have a layer of aquifers, so of transboundary aquifers, those 600 aquifers that I mentioned before, and we can see which aquifers studied by whom. There is another field here, studied aquifers, so that you can see where researchers who study a specific aquifer are anybody in the world, where they're in the world. But the most interesting part is to actually visualizing the co-authorship network. So here I just zoomed into one of the large clusters, and this is Sharon Mcdowell at University of Arizona, who built quite a school of transboundary research. And for any person here, what I just showed was a list of coefficients that indicate her role in the network. We can also subset it by any of the additional keywords, such as modeling. So here are everybody who's done modeling work. And now I'm trying to see how this research and modeling has evolved over time. So you see, I move in the slider, and you can see how those clusters of researchers started to grow, how they started to join other clusters, how people from other countries joined in this research theme, and you can see these dynamics for the entire world. You are very welcome to try it yourself, following the links in the chat. But this is just the last slide to kind of share some thoughts about how you can use it. You can explore the entire international academic landscape, whether you're working on transboundary groundwater or another water topic, or any other topic generally. You can analyze how research clusters developed over time, how they expanded due to the addition of people from other countries or other disciplines. See what topics started to emerge, which topics became prevalent in the last few years. You can look at individual members and see how their centrality or key player indexes changed over time, whether they increased or decreased. And that also gives a way to provide objective impact estimate for projects that are specifically designed to build a network. You can see how successful your network building efforts have been if you can see that the network became more cohesive, or the members that you invested in increased their network profile. Finally, you are very welcome to try it yourself, as I said, and follow these links to learn more about our project and work with the galleries. Thank you very much.
Wonderful. Thank you so much, Ilya. And next up, we have Jeff.
Hi. Okay. My screen's okay.
It's good.
Yeah. All right. So I'm just following up a little bit from Ilya's presentation. So I'm also part of the Transboundary Groundwater Resilience Network, where in one of the, when he was talking about the bottom-up aspect of building the network, we had this workshop where we brought together all the different network members or researchers in transboundary groundwater, and we wanted to have a group modeling session with them. And I'm going to talk a little bit more about the kind of tools that we use for called systems thinking and participatory modeling. So just as a primer, what is systems thinking? Systems thinking is, it's more about a holistic and interdisciplinary approach to studying complex problems like groundwater systems. And the emphasis here is on the interaction of various variables, which are often nonlinear and have feedback relationships, right? So this is very typical of the interactions between human and hydrological systems. And group model building specifically, it's a type of participatory modeling method that combines systems thinking, facilitation, as well as system dynamics modeling. And it's a process of stakeholder engagement to understand and address complex problems and collaboratively develop strategies. So oftentimes with problems that involves communities, such qualitative modeling using systems thinking is a very useful approach to that. So we piloted this for TGR. It was a 2-day interactive workshop with 15 members from the network. And these were researchers across various disciplines, like what Ilya has mentioned. There were hydrologists, data scientists, some system scientists, as well as social scientists. And we introduced them to systems thinking and causal loop diagramming, to the basics of the tool. And the objective of that group modeling session was to build a shared understanding of the drivers of groundwater depletion across disciplinary boundaries. So I'm just going to very briefly share what the outputs of that. We essentially collected a mental model of the system. So in their model, they generated stuff that's got to do with the hydrological feedback, which is the representation of the water cycle, as well as the dynamics between surface water and groundwater, which are all the black links in this model here. And then there are also the human effects here that's represented by the blue links, where they look at water demand as well as water withdrawal due to household, industrial, as well as agricultural consumption. And they also went into a discussion on the political conflicts between territories, right? Because trans-boundary water resources, there were also some tensions between countries, as well as adherence to international treaties and whatnot. And also, more importantly, they wanted to explore the climate feedback as well. So the researchers were very interested in environmental and climate impacts on groundwater, more on climate-induced migration, pollution, land use, as well as accelerated evapotranspiration. So the idea of this session was to then obtain the different, integrate the different perspectives that each researcher brought with them from their disciplinary silos, and to integrate them into a bigger model of the system surrounding groundwaters. And after the workshop, we had an evaluation survey where in general, we found that the participants found the modeling process to be very useful in broadening their insights on groundwater resilience. And also they believed there was a good representation of the collective mental model, which obviously could have been strengthened with more extensive deliberation. So what are some of the benefits or the potential of a group model building as a method? First, it's a very useful method to facilitate interdisciplinary collaboration because system dynamics as well as group model building, it is domain agnostic, right? So it's a method rather than a discipline. So it also has very accessible and unifying language that works across disciplinary silos, and it's useful to exchange and integrate perspectives. The model then functions as a boundary object. What I mean by boundary object, it means that it's an object that is able to be, that's transformable by the group based on deliberation and exchange of information, as well as it's a kind of object that is able to integrate the perspectives without really excluding perspectives that are not collectively shared. And here it was more of an integration of the water, social, as well as data and system science, as I mentioned earlier. But in the future, this can also be used to integrate perspectives from other community members, practitioners, researchers, as well as policymakers. And it's another tool to enhance knowledge production because this integrated mental model, when we validate this, it could serve as a knowledge repository. So what we usually do once we get the local knowledge or the people in the room, once they put it together, we carry on with then trying to validate the models that they have built in the room with literature. And it also could lead to a richer conceptualization of the system and feedback relationship. Oftentimes, like for example, in this workshop, in a lot of quantitative models, we tend to leave out more of the political or the softer elements of the system. With this kind of qualitative modeling, they're able to explore areas that are typically left out of the typical quantitative model boundaries. And it also helps to build a shared understanding, which then becomes a prerequisite for setting priorities for action. So we always talk about mental model alignments. When we want people to work towards solutions, we want to put them in a room, get them to deliberate. Getting a product like this creates the shared understanding, which then can be used for further policy actions. And the other thing is that it also provides a groundwork for simulation modeling. So because this is a qualitative model, this helps to define the model boundary, or at least pick up key variables that the communities themselves envision to be important and that should be included in quantitative models. And importantly, then I also identify local knowledge gaps as well as data collection needs. So I think this will be a segue a little bit to AI. So in the typical sense, we usually start with qualitative modeling work, which we then translate into
just about 1 minute left, Jeff. You can wrap up. Thanks.
Quantitative modeling, So with AI, that's where you use with data collection. But now with language models, like for example, here I use ChatGPT, and it's also able to build causal loop diagrams using the language models. So there is a potential because AI is able to do quick, there are AI tools that does literature review that can generate a very comprehensive list of variables in the system under study. And that can also then, does that mean it can replace group model building? One of the problems with this is that it's quite black box. We don't know what is actually going on in the behind the scenes for the knowledge production. And then there's also this reproduction of biases because there tends to be a more quantitative bias in the literature. You're going to also lose out the kind of soft variables that stakeholders might be interested in. And then you also reproduce the local knowledge gaps. And also excluding communities in the modeling process then also reinforces this scientism where you believe or you trust the AI without really including stakeholders within the research. But I don't think that it's meant AI is going to completely disrupt qualitative modeling. In fact, I think it could be complementary, where now AI generated knowledge could be used as a seed structure that can be validated with group model building. So participants can actually review existing variables and connections developed by the, like for example, ChatGPT, and then we can carry on with the normal group model building. This could be much more expedient. And by also then validating this models, local knowledge could be used to supplement stuff that's missing or stuff that's not relevant to specific contexts of communities. Yeah. So
sorry to interrupt, Jeff. We're about right at time.
Done. Yeah. So these are just like some of my reflections on some of the possibilities of AI and group model building in the future. Yep. Thank you.
Okay, wonderful. Thank you so much, Jeff. That was really insightful. Next up, we have Julie.
Okay, can you see my screen?
Yes.
Okay. Hi, my name is Julie Christopher. I'm a technical project manager at the Supercomputer Center at UC San Diego. I currently support a number of projects, including the West Big Data Innovation Hub, TGR, and FAR. And today I'm going to be presenting on FAR. FAR is a research coordination network that focuses on the FAIR principles as they relate to ML, AI readiness, and reproducibility. So FAR is a NSF-funded research coordination network led by PI Christine Kirkpatrick, Karen Stocks, who's on the call, Daniel Katz, and Douglas Rao. This RCN focuses on promoting better AI practices, especially related to data and research object management, improving efficiency and reproducibility, and exploring research gaps and priorities for data-centric AI. Machine learning and other big data synthesis and prediction techniques make it possible to use AI for decision-making. With pivotal technological advances and the emerging field of data-centric AI, robust research needs to occur alongside these innovations in several other dimensions. For example, an understanding of the relationship of FAIR data to ML accuracy and performance, the reproducibility of ML output, and how this varies between software stacks, hardware processor types, and environmental effects, and how researchers leading data facilities can make it easier to use ML on their collections. The researchers studying these areas need sufficient collective organizing capacity to keep pace alongside ML adoption. So what was our motivation for creating FAR? These are some of the guiding questions that we've developed to drive us further on our research and discussion in this space. So what if 80% of our time as researchers with data is spent wrangling it? Can FAIR principles be used to increase efficiency of people and machines? What does it mean for a repository or an organization to be AI ready? What roles can repositories play in AI readiness? And what community practices in AI, what are community practices in AI reproducibility, and what are the gaps in current knowledge? So these are just like a very broad overview of the FAIR principles, which are findable, accessible, interoperable, and reusable. This slide is an overview of these principles, and thanks to FAIR, we can generate and encourage open access to data and metadata. These guiding principles help our discussions on what it means to be AI ready and to enable reproducibility. Reproducibility refers to the ability of a researcher to duplicate the research results of a prior study using the same materials as were used by the original investigator. So AI reproducibility specifically is complex and resource intensive. This includes original researchers prioritizing key aspects of their data to document, lack of awareness of the reproducibility issue, and papers older than 3 years can typically be outdated or the data can be difficult to find.
Sorry to interrupt, Julie, just about a minute left.
Okay, the intensive part is the researchers' extra work to make it reproducible and the library personnel who want to help. So I'll just go through this real quick. This is just an example of AI irreproducibility. Sorry, it's a tongue twister. And then, so these are our goals. Big overview is promoting better practices for AI, harnessing community efforts, improving efficiency and reproducibility, stimulating and enhancing new research. And then our activities include workshop, webinars, assessing community needs, research agendas, and creating community-led reports. So we have an upcoming webinar tomorrow, August 22nd at 8 a.m. Pacific time. And this webinar is led by Dr. Odd-Erik Gunderson and Kevin Cookley. So I'll add the link to the webinar, and then I'll add a link to more details for you to read later if you're interested. This is our FAR team, who I will pass it off next to Karen. So I just want to say thank you to our team and to all of our partners. Thank you.
All right, I think I will flow right in then. Before I get started though, I'd like to get a feel for the room. If all of you could take a moment to find that reactions button at the bottom of Zoom. And if you feel like you're familiar with the FAIR principles for data, that's FAIR, F-A-I-R that Julie was just talking about, give a thumbs up. Okay, I need to scroll through. Okay, that's good to know. I can move through that a little bit faster then. All right, I will share my screen now. Go into slideshow. All right, so following on from Julie's talk, I'll be presenting a little bit more specifically on how we're looking to use FAIR principles to support AI-ready data. I'm a data repository person. I come from the oceanography world. So Julie has already introduced FAIR, and several of you are familiar with it already. We've got some links here. Essentially, the FAIR principles lay out not just the goals, but some specific steps that data repositories or other with data or other digital assets can take. So for example, within Findable, the goals are to have unique and persistent identifiers for data and metadata, have very rich metadata, connect data and metadata with the identifiers, and have all of that findable in a registered searchable resource. So note that these are not prescriptive as far as technologies go. It does not say what metadata standard you need to use, just that you have to have one. It doesn't say where to register your data, just that it needs to be registered. So I wanted to take a minute to reflect on how these principles are supporting a machine learning or AI readiness perspective. It does say, like, for example, with findability, that the digital resources need to be able to be found not just by humans, but also by computers. and that extensive machine actionable metadata are necessary for that to happen. With respect to accessible, there need to be protocols for retrieving those digital resources, not just GUIs for humans, but API kinds of things that are machine actionable. With respect to interoperability, it should be possible for machines to merge data from more than one source. So the format, the contents need to be well enough understood and described in a structured enough way for that to be clear. You should also be possible if there are tools that are available and data that are available, when those tools can apply to those data, it should be possible to sort of create those workflows that can automatically know which are compatible and how to call them. And finally, for reusable, it should be clear, what the use constraints on the data are, what the citation that's needed is, things like that. Okay, so that's kind of the dry side of the talk. Now a little bit of motivation. I'm not sure how many people on the call are familiar with HydroShare. This is an online data and tool portal. It supports mainly models and data around water science, but it's been built from with a strong focus on the FAIR data principles, and that enables some nice capabilities of the system. So if you go there, you can do a search, as you can in many data portals. Having just had Hurricane Hillary passing through, my search was on stream flow prediction in California. That seemed timely, but you get a set of responses back. You can see them on a map. This is pretty standard stuff. If you click on one, you get more information about it, including download links and stuff. But if you look over here, you can see that it also has tools that are lined up. And depending on the type of data that you have, or if it's a notebook, the type of resource, there are tools here that you can automatically feed those data in and use with them. And there are other apps as well. And this is what we were talking about with those FAIR principles, that if you describe your data well enough and structure it well enough and have these machine readable components, you can enable some of this automatic tooling. It also is enabling machine learning studies as well. This is an example of one based on corn yield. If you scroll down on that, you can download the data, you can download the code. This is shared with the community, so then it becomes available for others to build forward from. And in fact, if you do a search on machine learning in HydroShare, you can see there's a growing set of resources that come back. And this is just the set of those that had machine learning prominently in the title or in the description. So that's a real quick fly through. If you're interested in anything we've talked about here in this area, in learning more, in finding community and contributing, please feel free to contact the project as a whole. And I'll also put my individual email in the chat. I'm happy to have those comments. All right, thank you very much.
Thank you so much, Karen. I just want to take a moment to thank all of our presenters. I think we're right about at time, and I think a lot of the questions were answered in the chat throughout, but we just want to be sure to let everybody know. We've been posting the links throughout, but if you're interested in staying engaged after the event, we encourage you to fill out the Google form. So you can either use the QR code or the shortened link below to get there. And after the event, we're going to be posting additional resources at westbigdatahub.org/World Water Week. And so we look forward to talking with you all more and engaging in the future about these emerging issues. So thank you so much, everybody, for your time. And thank you again to our presenters.
Thank you.
Thank you.